All right, so we're starting here with Chapter 6, Section 1, Day 1. We're actually going to split this up over 2 days for the notes. And the first one we're going to talk about is antiderivatives in slope fields. So first, let's take a little review. We're going to consider the fact that y equals x squared plus 3. Well, if we take its derivative, we're going to get y prime equals 2x. Well, if we have x squared minus 5 is equal to y, then y prime is also going to be 2x. So here's the situation. We have two very different functions with very different locations on the coordinate plane that have both exactly the same derivatives. So what that means is that for any point along the coordinate plane, well, actually any point along the x-axis, for any value, we're going to have exactly the same slope for this one as we do to that one. Now, that tells us only about the slope. It doesn't necessarily tell us about what the thing's doing and all kinds of things like that. So notice it doesn't matter whether the constant was 3 or negative 5, since when we take the derivative, the constant's going to disappear. Now, however, when we try to reverse the operation and go from y prime to y, if we have y prime equals 2x and we're going to find y, well, we get y equals x squared plus c. And if you remember, we did talk about the plus c a little bit, not much, but the plus c takes the place of this constant here that may or may not exist. It may be 0, in which case the c doesn't exist. Now, we don't know what the constant is, so we put a c in the answer to remind us that there might have been a constant. There probably is a constant. The case is the constant may have been 0, so it wouldn't have actually been there. Now, if we have some more information, we can actually find what c is. For instance, let's say we have that exact same derivative, y prime equals 2x, and y equals 4 when x equals 1, and we want to find the equation for x. So we're going to take the antiderivative of this. Antiderivative of y prime is going to give us y. Antiderivative of 2x is going to give us x squared plus c. So once we have the x squared plus c, we have a situation here where we know that y is equal to 4 when x equals 1. So if we plug these two pieces of information in, we can actually find out what c is. So we plug in x, 1 for x, and 4 for y. And when we solve that, we got 4 equals 1 squared plus c. Subtract 1 from both sides, and c is going to equal 3. So our equation here, then we take this c, plug it in right there, and we find out exactly what our equation is. Now, real quick, this is what's called a general solution. It's the general solution to this differential equation. A differential equation is an equation that has a derivative in it somewhere. Now, if you've looked ahead into your college planning and you're taking something, you're majoring in something that's very technologically based or scientifically based, you probably know that as soon as you get done with the calculus series, you take a class called differential equations. Well, that's primarily what it's dealing with. Not this easy, but you're dealing with equations that have derivatives in them, and you're finding the general solutions, and in some cases where we're given an initial condition, we can find what's called the particular solution. So the general solution is the solution for all values of c. The particular solution is where we actually have a piece of information, usually a point on our graph, that's going to be able to allow us to find what c is. Now, this right here is called an initial value problem because we actually are given the initial value that we need to find what the constant is. An equation containing a derivative, as I just said, is called a differential equation. It becomes an initial value problem when you are given the initial condition and asked to find the original equation. This is the original equation. This is not a general original equation. This is a group of equations because remember the C is nothing more than a vertical shift, whatever we add there. Whether it be a positive or negative, it's just telling you how much far up or down to go. And we're going to see that in just a second. All right, now initial value problems and differential equations can be illustrated with what's called a slope field. And it is exactly what it sounds like. It is a field, it's a coordinate plane that becomes the field that shows you all the possible slopes for all the possible points. Or at least gives you an idea of them. All right, slope fields are mostly used as a learning tool and are mostly done on a computer or graphing calculator, but they have actually started putting them on AP exams and asking you to find a simple one. Usually it's going to be 9 or so points, and you just evaluate what the slope is at each one of those points. It's not very difficult. All right, so for instance, let's do a slope field for this differential equation we've been looking at, y prime equals 2x. Now, guys, here's what I want you to remember. Remember that y prime is another way of saying dy dx. And dy dx is another way of saying slope. So the slope of this equation, of the original equation of this graph, is 2x. 2 times whatever x value is for a given point. So for instance, we can go in and we can put in all these different x values and y values for all these different points, and we can find out what y prime is. Now I'm going to pause it for just a second, and I'm going to put points at all the points that I'm going to find. Just put little dots there so you can actually see what we're looking at, and then we're going to go back and we're going to put these all together. So just hang on. All right, so this will give us an idea of what we're dealing with, and this is going to be quite a few points. It's actually going to be more points than they typically will ask you to do on an AP exam, but they're going to be really easy, so it's not a big deal. The reason they're going to be easy is we're going to explain it in just a second, but we're only going to have to do this in one direction, really. And I'll explain why once we see it. So let's go ahead and get some points here. Let's go ahead and go across here, and we're going to have x equals 1, y equals 0, and x equals 2, y equals 0. Actually, let's change that. Let's go ahead and do 1, 0, 1, 1, and 1, 2. And I'm not going to do these down here. Let's go ahead and do that. Let's do 1, negative 1 instead of 1, 2. But I'm only going to do 3 of them in each x value. All right, so when we find y prime, which once again is the slope, when we plug in x equals 1 into this, we're going to get 2 times 1, and 0 here has no effect on that. Y prime is not equal to y, so you don't put a 0 over here. So 2 times 1 is going to give us 2. What you're going to do is you're going to go over here to the point 1, 0 right here, and you're going to draw a little line segment that has a slope of 2. So roughly that'll be about that. All right, and when we do 1, 1, once again we're going to take the x value, plug it in right there. 2 times 1 gives me 2. This value doesn't have anything to do with it, so I'm going to have another line segment that has a slope of roughly 2. And guys, I'm not going to get a ruler out and measure to make sure that you're, tilted in the exact right way or anything, but just make sure it's kind of close. All right, and when I do 1, negative 1, once again, I'm going to take this x value because that's the only thing in here that I'm based on, and 2 times 1 gives me 2. Once again, still a positive 2. Now, in case you haven't picked up on this yet, x is the only thing that affects the slope. So as long as the x is the same value, what do we know? The slope is going to be the same value up and down and side and all over. So that means that we're going to have a slope of, wow, that's awful. Slope of about 2 there, a slope of about 2 there, and a slope of about 2 down here, etc. So it's going to keep going over and over and over again. Because my equation, my differential equation here, is based only on x. If this had been 2xy, then it's based on both x and y, and as my y changed as I went up and down, my slope would change as well. But since it's just 2x, it doesn't do that. All right, so let's move over to right here, and let's do the 2's. And I'm going to do 2, 0, and 2, 1. I'm not going to do 3 of them this time. So when you plug in 2 here, you get 2 times 2, which gives you 4. That 0, once again, has nothing to do with it. Same thing with this. I'm going to get 4. So when we write our equation, our line segments here, we have to be steeper. We have to have a slope of 4, or a steeper slope than we had over here at 2. All right, and let's go back here to 0. So let's do 0, 0, and we'll do 0, negative 1, because as we know, the y value doesn't matter. It's not changing anything with this one. So if we do 0, 0, we're plugging in 0 right here. 2 times 0 gives me 0. That means I should have a flat line segment right there. And 0, negative 1, I'm still plugging in just the x. 2 times 0 gives me 0. I'm going to have a line segment that is flat there as well. And it's going to be flat all the way up and down. All right, and then I can go over here to negative 1. And I'm just going to do negative 1, positive 1. We plug in the negative 1. 2 times negative 1 gives us negative 2. So that means that at negative 1, positive 1, I'm going to have a slope of negative 2. So roughly the same slope here, but in the negative. It's going to be the same all the way up and down. And then if we get over here to negative 2, let's say we're doing negative 2, negative 2. Now let's do negative 2, positive 2. So we're dealing with this part right, this point right here. And once again, guys, it doesn't matter with this problem what my y value is, because all the values up and down are the same, because this is based only on x. So if I plug in negative 2 here, 2 times negative 2 gives me a slope of negative 4. So these are going to be really steep, not steep enough, really steep over here. No, probably not steep enough either. All right, now here's the thing. Remember what these lines are. These lines are nothing more than what the slope is at any given point along the way. So let's say we had a point right here. What happens as I go over this direction, in the x direction? Well, my slope has to go from 0 to 2 to 4 as I get further and further away. So what's going to happen with that? Well, I'm going to have something that looks like that. So it's going to be a parabola. Now what do we know our solution here was? All right, well, our general solution was what? X squared plus c. So the only thing that determined what my c was what the point that I was given was. So that's what we're looking at here. The equation, the differential equation, is going to give us a slope field. The slope field is going to give us the general behavior of every single point along the way. We could have just as easily had a graph down here that had a point of 0, negative 2. And guess what? The slope behavior is going to be very much the same. It's still going to be what? A parabola. So that's what we're looking at when we're looking at slope fields. And slope fields are really easy. We're just taking it point by point by point. All right, so let me put all these in here. And if you know an initial condition, such as 1, -2, so we've got a point right here at 1, -2, we can identify what that graph's going to look like from that point just by following what the slopes are. All right, now for more challenging differential equations, we'll probably use the calculator to draw the slope field. I'll be honest with you, there are very few of the slope field problems that you're going to have on the AP exam that you'll need a calculator for, but I do want you to know how to do them just in case you need them in college. So let's, for instance, say we're looking at the differential equation dy dx is equal to negative 2xy over 1 plus x squared. Now, just to kind of draw a relationship, and yes, I know this is a lot more difficult than the one we just looked at, but more specifically what I want to point out is the fact that since we have both x's and y's in this over here, we know that we're not going to have vertical columns that are all going to have the same slope. As y changes, this slope is going to change in the same way that it changed in that last one as the x changed. So since we have both x and y here, it's going to change as we go up and down, and it's going to change as we go side to side. So on the TI-89, if you want to see the slope field, you're going to have to make some changes to the graph. And you're going to go to the mode and change the graph type to differential equations. Now this does not work for the 84. For the 84, you actually have to go and get a program that would do slope fields, and I would really double check on that to make sure that it's right, because there are some of those that I have tried for the 84 that do not give the correct slope field. So you got to be careful. This one is actually programmed from factory, so it's right. So go to mode, change the graph type to differential equations, and when you hit diamond and Y for you to put in your equation, it's going to look a little different. Now you can do the delta. Once you get to the Y equals, do your diamond and vertical bar and make sure fields is set to slope field. For the most case it will be. But when you go to the diamond and Y to put your equation in, you're going to notice you've got y1 prime. Well, there's your differential equation. This is dy dx, the derivative of y. And you're going to need to put in t in place of all your x's, and you're going to need to put y1 in place of all your y's. It's just the way it's programmed. That's what you have to do. And it's the reason why is because they're going to have to do something, because x corresponds to x on the graph that it's going to put it on, but t is a way that we can actually get around that. So put in t for your x and y1 for your y's. And right below that, you'll have a yi1, leave it blank. All right, and you can adjust your viewing window. This is going to give you the window that is exactly what it's going to show here, but that's what it gives you. It'll give you a situation like that, where it is showing you from, now notice you're doing T-max and T-step and T-plot, and then X-min and X-max and all those things. These settings are what gives you the resolution, the length of your line segments, and things like that. Those are good settings. I would leave them just like they are. Your X-min, X-max, that is literally just the same way we've always looked at it. That is the dimensions of the graph. X-min, X-max, Y-max, Y-min, etc. And it'll show you all the dimensions here, and it shows you all the little slopes. Now, be sure when you do that that when you go out of that and you're not graphing differential equations anymore and slope fields, change your graph type back to function. Now, integrals such as the integral from 1 to 4 of x squared dx are called definite integrals because we can find a definite value for the answer. Now, if you remember, we went back and we were looking at these in the last chapter, and we were estimating what these values were by finding the area under the curve, or by approximating the area under the curve with both rectangles and trapezoids and other ways. Now, we can also use the antiderivative to find that. So what's the antiderivative of x squared? Well, that's going to be 1/3 x cubed plus c. And we're going to evaluate this from 1 to 4. Now, when we put the plus c in there, notice with this one, we put in 4, and we put in 1, and we have c minus c. These are going to cancel out. So what that leads us to understand is that the constant will always cancel out when we find the definite integral, so we don't have to worry about it. Now, if you're doing an indefinite integral where you don't have the upper and lower bounds, and you just end up finding an antiderivative, you must include the plus c. If you don't, it is incorrect. When you're finding a definite integral, since the c minus this c will cancel out, minus this c right here, we can leave it out and forget the plus c on definite integrals. But don't forget them on the indefinite integrals without an upper and lower bound. All right, and speaking of indefinite integrals, integrals such as the integral of x squared dx are called indefinite integrals because we cannot find a definite value. We don't know where this thing starts and we don't know where this thing ends. So if we can't find a definite value for the answer, that's where we need to leave the plus c in there. So 1/3 x cubed plus c. When finding indefinite integrals, we always include plus c. Guys, when in doubt, put plus c. All right, many of the integral formulas are listed on page 332 of your textbook. The first ones that we will be using are just the derivative formulas in reverse. Now, at first, we're going to do simple integrals that are just those things in reverse, but then we're going to get the more complicated in the ones that would have functions inside of functions and all kinds of things like that. So it's going to get more complicated, but those are the basic ones that you need to start learning right now. All right, the book shows a technique to graph the integral of a function using a numerical integration formula. That thing takes forever, and you don't typically have to graph the integral. It's a lot easier to take the indefinite integral and then graph it. All right, so to find the indefinite integral on a TI-89, you're going to use the integral thing. So do the integral. It'll open the parentheses. You put in the thing that you want to find the integral of, indefinite integral of, and then comma x and close parentheses. This will give you back the antiderivative of that, sine x minus x cosine x. Now we're going to learn how to do this by hand, but I want you to know how to do it with the TI-89 as well. Now, notice that this is different from how we did the definite integrals. With the definite integrals, you would have put comma 1, comma 4, where those are the lower bound and the upper bound. In this case, we don't have bounds, so we don't end up putting those things. Now be careful, because notice that the calculator leaves out the plus c. You have to put it in there because this is an indefinite integral, so it would require it. Now, if you wanted to graph this thing, you've already taken your antiderivative, then you could put that thing in there and graph it, and that's what it looks like. Like I said, you're not going to have to graph indefinite integrals very often, if at all. So don't worry too much about that. All right, now any two solutions to the differential equation dy dx equals 5 are parallel lines. True or false? Well, if we've got the derivative is 5, that means that the slope is 5, and that means that any function that's going to have a slope of 5 is going to be parallel to every other thing that's going to be parallel. It's going to have a slope of 5, so that is true. They are all going to be lines of the form y equals 5x plus c, so it's true. All right, if f of x is a solution of dy dx equals 2x, then f inverse of x is a solution to dy dx equals 2y. Now, remember, we're always aware of the fact that when we do an inverse, x's and y change parts. There's only one problem. We're talking about the slope here. We're not talking about the actual function. So we've got to be real careful here, and this is not going to be true. For example, this is saying that f of x equals x squared is a solution of dy dx equals 2x. But f inverse would be the square root of x, and it is not a solution to dy dx equals 2y. So we could get a couple of examples and see if it truly worked out. And if there's one case where it doesn't, then it's not a solution. So there's our justification right there. So this would be false. All right, a slope field for the differential equation dy dx equals 42 minus y will show a line with a slope of -1 and a y-intercept of 42. A vertical asymptote at x equals 42. A horizontal asymptote at y equals 42. A family of parabolas opening downward, and a family of parabolas opening left. Well, here's the thing. When y equals 42, what's going to happen to the slope? It's going to be 42 minus 42, which is going to be 0. So the slope would be 0 when y equals 42, and that's going to give us a horizontal asymptote at y equals 42. So that's your answer. Remember that dy dx is the slope, so when you're looking for clues as to what it's going to look like, find out where the slope is going to be 0, where the slope is going to be undefined, things like that. That's going to... All right, so this one says, for which of the following differential equations will a slope field show nothing but negative slopes in the fourth quadrant? Now, remember what we have in the fourth quadrant. In the fourth quadrant, we have x values that are positive, we have y values that are negative. Down here. All right, so x values are positive, y values are negative, and all we're doing is we're just going to plug these signs in and see which one of these, there should only be one, are going to give us nothing but negative possible values. So if we plug it in right here, we're going to have a negative, that's this one, and then a positive divided by a negative. Well, what positive divided by a negative gives us a negative. We have this negative times that negative, which gives us a positive. So we know it's not that one. All right, if we have a positive and a negative here, we have a positive times a negative, which is going to give us a negative. And then we add 5. Well, it depends. If this product of x times y is greater than 5, it's going to be negative. If this product of x times y is less than 5, it's going to be positive. So this one is sometimes positive and sometimes negative. So, and we're looking for nothing but negative slopes. So we know that one's not it. All right, when we plug in our positive and our negative right here, we have a positive here, negative y squared. A negative squared gives us a positive. Positive times a positive gives us a positive. And then the positive minus 2 is going to equal, well, what? Well, if this product right here is less than 2, it's going to give us a negative. But if this product is greater than 2, it's going to give us a positive. So it's going to give us both, and we're looking for nothing but, so that's not it. And then if we plug in here, we've got positive times a positive times a positive gives us a positive. On the bottom, we've got a negative times a negative, which gives us a positive. So that's always going to give us a positive. And then down here at the bottom, if we have a negative over a positive, we're always going to end up with this part right here, negative divided by a positive, being a big fat negative. If we have a negative and we subtract 3, well, if it's always negative and we're always subtracting from it, it's always going to be negative. So E is our answer. All right, which of the following differential equations would produce the slope field shown below? So here what you want to do is you want to look at all your possibilities here. And one of the ways you can do that is you can identify in different quadrants. So do a quadrant 1 with 1, 1. Do a quadrant 2 with negative 1, 1. Do a quadrant 3 with negative 1, negative 1. And do a quadrant 4 with 1, negative 1. And when you put those 3 in, is it giving you slopes like what you're seeing here? So right here, should they be positive or negative? Well, they're looking like they're positive. So at that point, I should expect a slope that's positive. Right here, I should expect a slope that's negative. Not large, but it should be negative. Right here, definitely negative, big numbers negative, and the same thing here. Now, if that does not eliminate all but one, then you can go back and you can do some other things. Like you could plug in the point right here, and what do we notice? That should be negative. You could plug in 0, 0. That should be negative, or that should be 0. Or real close to it anyway. And you could plug in points like all over the place, like negative 2 or 0, 2, and things like that. That's all you're going to do to narrow down your choices here. And don't get thrown off by the absolute value. It's the same thing we were looking into when we were looking at that x squared just a second ago. The absolute value of x is nothing more than the same thing as x squared as far as when we do the sign thing. It's always going to be positive. Now, once you do all that, your answer that you should come up with is that you should be able to eliminate everything except for A. Try this, because I guarantee you you're going to have a test question like this. Guarantee that you will. Go back and make sure that you can use points in all the quadrants to eliminate all of these except for A, because A is the one that actually works here. And you don't have to use the points that I used. You could use negative 2, 0 instead of, negative 2, 1 instead of negative 1, 1. Because it's a little more obvious there that that should be negative. You could do the same thing over here with 2, 0 or 2, 1. So you don't have to use those exact same points. I'm just giving you an example of what you would do. All right, that is all of section 6.1. We will pick up later. Write down any questions you might have and ask them first thing in the next time we meet.